Welcome to the Running Zone. I'm Mr. B. During this lesson, I will explain how to determine the delta H value for a reaction by using Hess's Law. According to Hess's Law, if a reaction can be carried out in one step or a series of steps, the sum of the enthalpy changes for the individual steps must be the same as the one-step process. Let's apply Hess's law to an actual reaction. Consider the following equation where 2 moles of sulfur dioxide gas reacts with 2 moles of solid phosphorus and 5 moles of chlorine gas to produce 2 moles of thionyl chloride liquid and 2 moles of phosphoryl chloride liquid. To assist in solving for the delta H of the reaction, we're also provided with 4 individual steps, where each individual step includes its own delta H value. The key to solving for the delta H of the original equation is to arrange the individual steps such that they match the original equation in terms of orientation and stoichiometry. In step 1, thionyl chloride appears on the reactant side. However, in the original equation, 2 moles of thionyl chloride will appear on the product side. Therefore, step 1 must be both doubled and reversed. If the step is doubled and reversed, the delta H value must also be doubled and reversed. So the original 10.3 kilojoules now becomes negative 20.6 kilojoules. In step 2, phosphoryl chloride appears on the product side. This matches the original equation. However, in the original equation, 2 moles of phosphoryl chloride is produced. Therefore, step 2 must be doubled. And the delta H associated with step 2 must also be doubled. Negative 325.7 kilojoules now becomes negative 651.4 kilojoules. In step 3, solid phosphorus appears on the reactant side. This matches the original equation. However, in the original equation, 2 moles of solid phosphorus is consumed. Therefore, step 3 must be doubled. And the delta H value now goes from negative 306.7 to negative 613.4. In step 4, 2 moles of chlorine gas appears on the product side. However, in the original equation, 5 moles of chlorine gas appears on the reactant side. Step 4 must be reversed. And if the step is reversed, the delta H value is reversed. So negative 202.6 kilojoules now becomes positive 202.6 kilojoules. Now cancel the intermediates, where intermediates are substances that appear on the reactant side of one step, but on the product side of a different step. This means that during the reaction, these substances are actually consumed. 2 moles of liquid water appear on the product side of step 1, but on the reactant side of step 4. 4 moles of HCl vapor appear on the reactant side of step 1, but on the product side of step 4. 1 mole of oxygen gas appears on the reactant side of step 2, but on the product side of step 4. 2 moles of PCO3 liquid appear on the reactant side of step 2, but on the product side of step 3. All these substances may now be canceled out. Notice that 3 moles of chlorine gas appear on the reactant side of step 3 and 2 moles of chlorine gas appears on the reactant side of step 4. At this point, we add the 3 moles of chlorine gas to the 2 moles of chlorine gas for a total of 5 moles of chlorine gas. If we now add the remaining substances in the 4 steps, we will indeed regenerate the original equation, where 2 moles of sulfur dioxide gas reacts with 2 moles of solid phosphorus and 5 moles of chlorine gas to produce 2 moles of thionyl chloride and 2 moles of phosphoryl chloride. The final step is to add the adjusted delta H values. So we add negative 20.6 kilojoules plus negative 651.4 kilojoules plus negative 613.4 kilojoules plus 202.6 kilojoules. So the delta H for the reaction will be negative 1082.2 kilojoules. This concludes my explanation of how to use Hess's Law to determine the delta H of a chemical reaction. Hopefully this video has been helpful. Thanks for watching.